So in this short video, we're going to see what is meant by tensors. Okay, so tensors. So there are two kinds of tensors. One is called a covariant tensor, and another is called a contravariant tensor. So I'll introduce some notation and then try to explain what it means. So a covariant tensor means it has a index, upper index. Okay, so let's say, so this is a, it has a lower index actually. So it has a lower index. And a contravariant tensor means it has a upper index. So I'll tell you what this means, start telling you what this means and start telling you why this is used, and then it'll probably start making some sense. So a tensor with no index is actually a scalar. Okay, so tensor with no index is actually a scalar. And a tensor with one index, okay, it can be a contravariant or a covariant index. Let's take a contravariant index itself. In this case, it's a vector. And a tensor of two indices is a matrix, and so on. Okay, so we can have higher indexes. This is called the rank of the tensor. So the number of indices is called the rank. Now, why do we have these indices? So what does this mean? So AI means, so supposing you have a, let's say you have a vector in Cartesian, let's say you have a vector in Cartesian coordinates, and let's say it is 3i or 3, let's say x hat plus 4 y hat. So the unit vectors I'm calling x hat and y hat. Now if you want to go from, so this is nothing but, so this is notation is suppressed in this vector form. So this means the, so if I were to write it like this, so AI, so this is nothing but, so AI1, okay, is going to be your number 3. Okay, A2 is going to be your number 4. Okay, and so on. So it's just a way of writing this. So this is the notation. This is the notation is used to denote these coefficients. But what happens now? The usefulness of these vectors come when you want to change from one coordinate. The usefulness of this tensor notation comes when you want to change from one coordinate system to another. So supposing I want to go from Cartesian to polar. Okay, so I'm going here to polar coordinates. So this was Cartesian. So I have to go to, let's say I'm going to polar coordinates. So no longer what happens, your unit vectors are going to be x hat and y hat, right? It is going to be something else. It's going to be something else. It's going to be r hat and theta hat, right? And we had worked out when we are doing curvilinear coordinates how the unit vectors. So supposing this was your coordinate system, Cartesian coordinates. So you're going from this system to this system, right? So this system. So when x hat, when it goes to, so when it becomes, this is the polar coordinate. Here it will be 3 r hat plus 4. Now this change from y prime to theta prime is going to get little squished or scaled, because when you are moving from one system of coordinates to another, what happens, there is a rescaling of the picture, right? Because you are changing from coordinate systems, so there is going to be a scale factor which adjusts the components such that the components have right values in that particular system of coordinates, right? It's going to adjust the components, because the components are not going to be the same, because here you have x, the unit vectors x, y and y hat, but here it's r and theta. So there is going to be a change, and that change we had already calculated in our curvilinear coordinate system. Here it's going to be r times theta prime. So the coordinate theta hat is going to be rescaled by a value r. So this was the scale factor. We had calculated that, all that using the relationship between the two coordinates, which is nothing but x is equal to r cos theta and y is equal to r sin theta. From this we had got all these relationships, but we are going to do this in a more simpler way in tensor notation. So this tensor notation is going to handle all this change of coordinate systems and all this rescaling business. What is the value of this component in this system, and the rescaled value when you go to the other system. Okay, because this is going to be, this tensor notation itself was found very useful in physics when we do relativity. Okay, when you are doing relativity, you are going from one inertial frame of reference to another inertial frame of reference, right? So in special relativity, you are going from one frame to another. So when you are doing these coordinate transformations, so you're going from one frame of reference, which means you're going from one coordinate system to another coordinate system, which is moving or doing whatever. Okay, so that in that case, this tensor notation is very useful, and it is very useful in general relativity, where you are going from one. So there the transformation is between non-inertial frames, right? So you're going from one frame of reference to another, and the frame of reference is not an inertial frame of reference, it's a non-inertial frame of reference. And Einstein actually gives a beautiful geometric picture to this whole business of so in a non-inertial frame, what it means is that there is a it's an accelerating frame. No longer the two frames have a constant velocity between them, but it's an accelerating frame, right? And this accelerating frame, what it means, when there is acceleration, there is a force, right? If there is an acceleration, there is a force. And in this accelerating frame of reference, he captures, he relates, Einstein actually relates the geometry of that space time that you're going to in that new system of coordinates, the non-inertial frame, the geometry, the curvature of that space time to this force or the acceleration, right? So there is a relationship between force and acceleration. So he actually says that gravity, right? Gravity is the force that causes this acceleration. So this gravity and this curvature of space time is going to be related. So when you're doing general relativity, all this tensor notation becomes very useful, because you are going to evaluate one quantity in one particular non-inertial frame, and then you're going to another non-inertial frame, and the curvature of these non-inertial frames are actually uh, captured by the geometry, right? So it's going to be captured by the geometry. So you can take a ball. If you're taking a ball, it's going to be if you're taking a ball with a large diameter, it's going to be less curved. If you're taking a ball with small diameter, the curvature is going to be lot more, right? It's going to be a lot more. So this curvature is going to be captured by these uh, anyway, so when you go to study general relativity, we will see all that. But I'm saying this because you need to know where we'll be using all this. That's why I'm saying all this. So it becomes very useful. So this notation becomes very useful in those cases. So let's get back to our business of defining these contravariant and covariant tensors. So a contravariant tensor transforms. So let's say we are going from Cartesian to polar, right? So Cartesian to polar, it is given by this relationship, right? So uh, let's say this is our x is equal to r cos theta and y is equal to r sin theta. So you should have your relationship between the two coordinates. And a contravariant tensor. So if you have ai, which is your contravariant tensor in your Cartesian coordinate. Now you're going to, let's say you're going to your new coordinate system. Okay, let's say you're going to a new coordinate system, a bar. Let's call it a bar. Now a bar is going to be dx bar I divided by dx. So there's a partial derivative. And the value in the old, so this is the value in the, so aj, so this is aj. So these are indices. It will have the dimension of, it will go as 1, 2, 3 and the number of dimensions we have. So here the new coordinate is nothing but you're going from x to r, right? So here you have to invert this and get a relationship for r, and invert it and get a relationship for theta. So you're going from, so from x and y you're going to r and theta. So that's what you're going to, right? So x to r and y to theta. So your I and j value will run from, I will run as 1 and 2 and j will also run as 1 and 2. So you take the, so you evaluate this, you will get your contravariant tensor. And your covariant tensor, okay, so your covariant tensor, this is your covariant tensor, it will transform this way, in the opposite way. So it transforms the opposite way. Notice that this bar is here below. Okay, so bar I'll put here. This is a new coordinate system you're going, right? So this is the bar, right? So here also you should have a bar. So the transformation relations work out this way for a contravariant and a covariant tensor. And what do you do when, so in a vector, for a vector, if you want to take the magnitude that is in a particular frame of reference or in a particular system of coordinates, if you have a vector, if you want to take the magnitude, what do? You take the vector and dot it with itself, right? You take the vector and you dot it with itself, you get the magnitude of a, right? Similarly in your tensors, so in tensors, similarly, if you want to find the magnitude of a tensor or find the scalar product, or if you want the scalar, so you just take is nothing but the vector, the contravariant and the covariant tensor. You just multiply the contravariant and the covariant tensor and you will get the magnitude. Okay, so you will get the magnitude. So this is what this is the usefulness of tensors. And we know that when we are going from, so there's something called the metric. So this is also something very important. So the metric. So what is the metric? So you would have remembered when we are doing curvilinear coordinates. So when we were doing curvilinear coordinates, the element, the space-time element, or so this was our differential element. And when we go to, let's say this was in Cartesian coordinate, the differential element in Cartesian coordinate. This is called, in relativity, this is called the space-time interval, or here we'll just call it a unit interval. Now when we are going to, let's say when we are, if we are in the same thing, when we are doing it in cylindrical, what we will do, we will get the scale factors, right? So this in cylindrical, what will happen, this will just become dr square will be there, right? And this will become r square d theta square, right? Remember that, right? So r square d theta square and dz square, right? So the scale factors get into the picture to rescale the values of the components, because you're going from one system of coordinates to other. The value is not going to be the same, the value of your components. So it has to be rescaled, right, depending on, and it has to be done correctly so that the value is preserved when you come back to your previous system of coordinates, and such that the when you calculate the magnitude in each system, it should be the same, right? So the magnitude cannot change from one, it cannot depend on the choice of coordinates, right? So all that, those conditions we take in, and we use the relationship, the equations that relate the relationship between these two coordinates, and we find the scale factor. So that is actually what gets into your metric. So if I have Gij for cylindrical, the metric is nothing but 1 r 1, and rest all the only the diagonal elements have values, okay, and rest is all 0. And if I have, let's say, spherical, Gij is going to be 1 r sine theta. You might recall all this from your curvilinear lectures, right? Curvilinear coordinates lectures. So these were your scale factors that you got from your for your spherical system of coordinates. So this is called your metric. So this Gij is called your metric. And so these are curvilinear coordinates. So what are curvilinear coordinates? The angle between each coordinate is 90 degrees. X, Y, Z, the angle between each of them is 90 degrees. And in cylindrical, you have r theta and z, angle between each of them is 90. In spherical, r theta phi, angle between each of them is 90. In such case, the diagonal elements only have values, and there is no, the other elements, they are called the cross terms, they are not there. But if you go to any other system of coordinates where it is not curvilinear, that is means it's not 90 degree with each other, you will have cross terms. So you can have so many system of coordinates. You can have a parabolic system of coordinates, hyperbolic, there are it just depends on what kind of coordinates you want to choose. So this is called the metric of the this is called the metric. So this Gij is called your metric, okay? Gij is called your metric. So it can be a if the indices are in the bottom, it's called your covariant metric. It is the indices are on top, it is called your contravariant metric. So the covariant and contravariant. And you can convert, let's say you have a covariant vector, sorry, a covariant tensor. If you want to make it into a contravariant, so this is a contravariant tensor. If you want to make it into a covariant tensor, you just multiply with the metric, and you will have your covariant, you will have your covariant tensor. So this transformation can be done. So if you have a reverse process, if you want to convert covariant to contravariant, that also can be done. So this is your transformation using the metric. Now, very importantly, as I said, this this is largely used in relativity, general relativity, and the curvature of the space-time that you will describe in general relativity by the it can be captured, the curvature can be captured by derivatives, okay? So you should have a way to take the derivative in one system, in one frame of reference, and the value of the derivative should transform when you go from one system of coordinates to another, okay? So for that you should have a formalism, and for that you should have some system of formulas. That is what is called your covariant derivative. So this is the most general derivative. So this covariant derivative is your most general derivative because it is not, the value is not dependent on the frame, the choice of coordinates or your frame of reference, because it has into its formula a way by which it'll, when you go from one system of coordinates to another, its value will change because it has to change, right? Because you're changing the system of coordinates, right? So when you change the system of coordinates, the each component value will correspondingly change, right? So it should have a mechanism by which that it captures that, okay? Because your curvatures, all these quantities are going to involve derivatives, and once you have a formula for the derivative, you can have you can, all your other quantities like your gradient, Laplacian, divergence, all these things can be calculated in terms of derivative. So this derivative is very important. This is called your covariant derivative. Its symbol is this. The comma represents, here you have aij, this comma represents your derivative. Okay, so this comma indicates that it's a covariant derivative, and here you are taking the covariant derivative with respect for a covariant tensor. Here you are taking it with respect to a contravariant tensor, and here you are going to see some new symbol. So what is this new symbol? This is called your Christoffel symbols. So this is called your Christoffel symbols, and this Christoffel symbols can be calculated this way easily from the metric. So I discussed with you what is meant by a metric. So metric I discussed. So it can be easily computed with this formula directly from the metric. Okay. So this is about the covariant derivative. So this is the general theoretical background you need to understand what is going on in tensors. So so that winds it up. So I hope you found it useful. So we'll be, in our channel, we'll be going on to do general relativity. So when we do that, you will see how all this tensor machinery becomes very useful when we are doing general relativity. Okay. So hope you found this video useful. So if you do like it, do subscribe, and also let your friends know that there is something like this. Thank you for watching.